Hello friends, good afternoon and welcome to Decide Live Lectures. Dear friends, as you know that we have started a series on phase equilibria and today we are conducting yet another lecture in the same series. In today's lecture, we will be talking about solutions. It will be third lecture on solutions. To discuss this topic, we have with us our subjects by Dr. Amit Kumar. Dr. Kumar is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome, sir.
Thank you very much, Amrit. Dear viewers, first of all, let me say very good afternoon to all of you. As you have been apprised of that in the series of phase equilibria, this is third lecture on the subtopic solutions. That is, we are talking about liquid solutions in particular and the equilibria between liquid phase and the vapor phase for a solution. All right, in this, if you remember, last lecture which we had, in that lecture we had discussed once a solution is formed and is equilibrated at a particular temperature, then it will result in, at a specified pressure, a particular value of total vapor pressure, and which will be a function of the composition. We had also seen a pressure versus composition graph and its nature we had discussed in detail. Let us have a little recapitulation of that graph once again, and so that we can proceed in our discussion in this lecture as well. Dear friends, if you remember, what we had discussed is that there is a linear curve between the 2 points PB0 and PA0, or A or B you can say. This linear curve is actually the total vapor pressure versus composition curve, that is composition in the liquid phase, this purple curve which I am talking about. And this blue curve, which is not linear, which is non-linear curve and is parabolic in nature, this curve is actually the total vapor pressure versus composition curve again, but composition this time is of vapor phase. And it is important to note that on the x-axis there lies the composition. This composition could be of the liquid phase, which is represented by symbol small xa, and this composition could be of vapor phase, which is represented by the symbol small letter y with subscript a, that is Ya, and is also the composition that has been represented between 0 and 1, that is amount fraction of component A or B. If we talk about the binary solution, then this capital Xa represent the amount fraction of component A in overall system. So, small xa means it represent the amount fraction or mole fraction of component A in the liquid phase, small ya represent composition or mole fraction of component A in the vapor phase, and capital Xa actually represent the mole fraction of component A in the overall system. So, this purple curve is basically relate the all the locus is this purple curve is the locus of all points which is the state point of the system at which a liquid phase starts to come at equilibrium. So, therefore, it relates the total vapor pressure of the equilibrium system with the composition in the liquid phase, whereas this blue curve is a curve between total vapor pressure versus composition in vapor phase. It is important to note that these two extreme points, this PB0 and PA0, these 2 points are common in between the two curves. This is the reason, that is, these two extreme points indicate the pure components. So, if there is pure component in the liquid phase, it will have same vapor pressure, that is, it will, a liquid of a particular component B would be in equilibrium with that with the same component in the vapor phase. So, therefore, their amount fractions would be of component B would be 0 when amount fraction of component A would be 1. So, it is something like this. So, then in that situation Pa naught would be 1, Pa naught would be the value of the vapor pressure of the system if there is only pure component A, and Pb naught would be the vapor pressure value of the system if there is only component, that is liquid B, which is being present in the system. So, what I mean to say is that this pressure versus composition curve is basically represent the pure liquid phase, pure vapor phase, and a liquid vapor equilibrium. Now, it is important to note that when we talk about phase equilibria, all the equilibrium systems in such studies, in the study of phase equilibria, is governed by the phase rule. And as per the phase rule equation, we know that degree of freedom is related to the number of components and number of phases present in the system by an equation, that is F degree of freedom equal to C minus P plus 2, where C is equal to number of component, P is equal to number of phases, and plus 2 is just a numeric value. So, it is important to note that we are talking only about binary systems, and when we are talking about binary systems, so our number of components would be 2 only, and if there is only liquid phase being present in the system, so number of phase would be 1. That is, both the components are present in liquid phase only. This would be possible only when the system is subjected to such high pressure that it does not allow any vaporization of the liquid at a specified temperature. So, in that case, liquid will be the only one single phase that is being present in the system, and C is 2, therefore P is 1. So, C minus P, that is 2 minus 1 equal to 1 plus 2 is 3. So, you will have total 3 degrees of freedom. What it does mean? It does mean that you can vary the temperature, pressure, as well as the composition. Since there is only one phase, that is liquid phase, so composition of overall system will be same as that of composition of liquid phase. What I mean to say is that if we talk about amount fraction of a particular component in a binary system, if there is only liquid phase being present in the system, so amount fraction of a particular component in liquid phase will exactly be the amount fraction of that component in the overall system. It means small xa would be same as the capital Xa value. It does mean that if we vary 3 different variables, the degree of freedom whose value would be 3 for such a system, it does mean that if we vary the 3 different thermodynamic parameters or the variables, then there would not be any particular change in the state of the system. It will not have any barring. It would, change of state means the system would remain only in one liquid phase. It would not change the number of phases in the system. For example, if you just have a look at the graph, and so that you can understand this point more clearly, you see above this purple line, purple curve, there is a whole area where my pointer is pointing out to be. Just have a look at this. All the points above the liquidus curve or the purple curve represent a big area, in which there are large number of points. This area is locus of a number of infinite number of points over here within this area, which each point in this area actually do represent a particular state of the system. So, what I mean to say to you is that the liquid phase would be stable over a large number of equilibrium states in the system. Number of, if you suppose for example, overall state point of the system is represented by this point, where at the moment my pointer is pointing out. Now from this, if you raise the pressure, all the points which come up above this point where the pointer is moving, all these points would remain in a way making it clear that there is only liquid phase being stable. So, there is no change in physical state of the solution. What is going to be a change is the only change in this system would be, state of system would be the change in pressure value being on which the system is subjected to. Similarly, you can vary temperature also, and you can vary the composition. You can see now here at the moment the pointer is pointing out at some point in this area, and if you add the component number A more, then the overall state point will shift towards x amount fraction f x a component 1, now where the pointer is travelling. So, it means all these locus of points would represent different amount fraction of component A in the system. Even then, there is, you can see, either you move horizontally or you move vertically within this particular area above this purple curve, you will have only liquid phase. So, it will not change the physical state of the system, that is liquid phase. So, it does mean that you have 3 degrees of freedom if there is only liquid phase exists. That is, you may change temperature, you may change pressure, you may change composition as well. It will not produce any change on the physical state of the system. Similarly, if we talk about the area below this blue curve, or in other words the vaporous curve, or in other words the curve which represents the curve between vapor pressure and the composition in vapor phase. So, below this curve there is again a big region, below this blue curve there is again a big region, and within this region you can move either from left to right or from top to bottom below this curve, blue curve or the vaporous curve. You will not observe any change again in the physical state of the system, which would remain only in vapor phase. So, it does mean that if you have the stability of only liquid phase and the stability of only vapor phase, then you have 3 degrees of freedom, that is the temperature at which, when you say that temperature has been fixed, for example, here this graph is being drawn at a fixed temperature, then you can draw the graph again at another particular temperature. So, when you say this graph you want to draw at a particular temperature, it means you have fixed one variable. You have specified the value of one of the physical parameter or thermodynamic variable, that is temperature. So, you had 3 degrees of freedom for each of the particular phase, either liquid phase or vapor phase being present in the system. In that situation, 1 degree of freedom you have used in terms of specification of temperature. Similarly, you can say the pressure of the system at which the system is subjected to is this much. So, then it means you have also specified the pressure, and at equilibrium whatever the pressure you specify will also be the vapor pressure and also the pressure exerted on the system. If there is a disturbance between, if there is not an equivalence between the two, system would not be at equilibrium. So, equilibrium condition require that the pressure at which the system is subjected to and the pressure of the system, the vapor pressure of the system has the same value. So, it means this particular second variable, that is pressure, has also been specified, and this means that you have used second degree of freedom. And the third degree of freedom, as you can say, we can let our system assume different compositions, even then the physical state of the system remains same. So is the degree of freedom is this is another degree of freedom, that is you can change the composition as well. So these are the 3 degrees of freedom which you can change over this vapor pressure versus composition curve. Now it is interesting as well as very important to understand what happens and what about the situation within these 2 curves, that is liquidus curve and the vaporous curve. There is another region that is called liquid vapor region. You see, within the region within these 2 curves represent a region where 2 phases are in equilibrium with each other, and these 2 phases are liquid phase and the vapor phase, which are in equilibrium. And when there are 2 phases in equilibrium, so therefore there will be different compositions of the 2 phases. As if you recall properly, at any given point being which represent the overall state point of the system within this region, if you draw a horizontal line which is called a tie line, which connects the 2 different phases, that is why it is called tie line, where this tie line or a horizontal line meets the 2 different curves, that is the liquidus curve and the vaporous curve. From those intersection points you can draw perpendiculars onto the x-axis or the composition axis, and in that situation from the composition axis you can obtain the amount fraction or composition of a vapor phase and of a liquid phase, which are in equilibrium, in thermodynamic equilibrium with each other. So what I mean to say is that in 2-phase equilibrium, if we apply phase rule and we can understand the situation in terms of phase rule, then we can say that applying the phase rule equation suggests that F degree of freedom equal to C minus P plus 2, and C again is here 2 because we are dealing only with binary systems. So C is 2, then P the number of phases here is also 2, as I said, within this liquid vapor region, that is the region between liquidus curve and the vaporous curve. This liquid vapor region is a 2-phase, is a region where 2 different phases are in equilibrium. So degree of freedom therefore F equal to C minus P plus 2, and C is 2, P is also 2, so plus 2, therefore you have 2 minus 2 plus 2, that is equal to 2. So degree of freedom is 2 for a 2-phase equilibrium, that is a region between liquid and vapor curve, and therefore in this region you can vary only 2 different variables. When you have plotted this graph at a particular temperature, when you have plotted the pressure composition graph, this phase equilibrium, this phase diagram at a specified temperature, then it means you have specified the value of one of the thermodynamic variable, that is temperature. So out of the 2 degrees of freedom, that is how many variables you could vary without producing any change in the physical state of the system. So out of those 2 you have used 1 degree of freedom in specification of temperature. Now you can fix only one another variable. That could be either the composition of liquid phase or of vapor phase, or you could fix the value of pressure. If you fix the value of pressure, then the composition will automatically become fixed. This point you can understand from the graph. So please have a look at what we are trying to say over here. If suppose this is the point which represent this dotted line represent the value of pressure at which the system is subjected to, and if there is the system is in two phase equilibrium. So, it means at this pressure, suppose this is the pressure. Now, at this pressure there is this or dotted line becomes a horizontal line which connects the two curves, liquid curve and vapor curve at point A and B. So, this point A is the point at which this dotted horizontal line cuts with that meets the liquid curve, and this line again cut or meets the vapor curve at point B. So, point A represent composition of liquid phase at this pressure and point B represent composition of vapor phase at this same pressure. So, what I mean to say is that if you fix the pressure and you say that whatever the overall composition be within this value A and B, it can be this point of composition, it can be this, it can be this also. Now, you can see from this pointer pointing out to be over here in the graph. So, overall state of the system can assume any different composition within these 2 points A and B. However, the composition of liquid phase would be this value given by point A and composition of vapor phase would be given by this point B at this particular pressure represented by this dotted line. So, that is all what we obtain from here. That is, we have 2 degree of freedom, one is being used in terms of specification of temperature and the other is being used in terms of pressure. So, that the amount fraction of component A in liquid phase and in vapor phase becomes constant or fixed. That is fixed by way of specifying the pressure and drawing a horizontal line from the pressure axis where it meets liquid curve represent the liquid phase composition, where it meets vapor curve it represent the vapor phase composition. Alright, so I also tried to make you understand in the previous lecture that if suppose we have only liquid phase and we decrease the pressure on this liquid phase, we continuously try to decrease the pressure on this liquid phase, then what happens that that can be done by way of increasing the volume of a system which is designed in a way that there is a cylinder fitted with a movable piston and within which the system is lying. So, if you increase volume, the vapor pressure decreases, so occurs a decrease in the pressure value. So, continuously when you decrease the pressure value, system try to makes up this pressure by way of vaporization. So, there a point occurs at which the first vapor starts to form, that is the maximum pressure at which the liquid can exist. And then when you continuously decrease the pressure, then a pressure as a result of decrease in pressure of the system continuously vaporized to a greater extent and more of vapors are formed. When more and more of vapors are formed, it leads to modification in the vapor pressure as well. But the volume gets increased continuously. So, therefore, vapor pressure also matches with that of the total pressure exerted on the system, and so that equilibrium is established. Continuously when you decrease the pressure in this manner on the system, a point reaches or a pressure point reaches at which you have only a last trace of liquid which remains, or you can say last drop of liquid which remains, and all the content has vaporized and filled the hollow space above the liquid layer and basically has led to the resulting of only vapor phase. So, this pressure will be the minimum pressure at which the liquid phase can exist in equilibrium with vapor. It is important to note. So, we have at any given composition we have a range of pressure within which the liquid phase is in equilibrium with vapor phase. There is a maximum pressure at which only a last trace of vapor remains. There is a minimum pressure at which only a last trace of liquid remains or a first bubble comes. We now switch on our attention to one very important point, that is lever rule. Basically, you have seen that we can understand which is the region of stability of liquid phase, we can understand which is the region of stability of vapor phase, we can also say in which region there comes an equilibrium between liquid and vapor phase. But now the question arises, can just by looking at this graph, can you say that how many moles are present in the liquid phase and how many moles are present in the vapor phase at a particular overall state point of the system? That is being given within this liquid vapor region. So, in that situation, we know that there occurs an equilibrium between liquid phase and vapor phase, but the question arises, can we understand or can we get to know how many moles of the system are present in liquid phase and how many moles are present in the vapor phase? So, or is there any relationship which relates the number of moles of liquid phase and number of moles of vapor phase? This is the question. This question is actually being answered by one very important rule, that is called a lever rule. So, let us try to see what is this lever rule. In order to understand the lever rule, we need to understand first of all from the qualitative picture only. Looking at the phase diagram, can we make some information out of this diagram so that we can say how the number of moles of liquid phase, that is one phase, is related to number of moles of vapor phase, that is vapor phase, that is other phase. So, this is the question. Let us have a look at it at the phase diagram. If suppose we have a tie line, as you have seen, this line segment AB is a tie line. I have already specified tie line is a horizontal line. First of all, let me tell you, tie line is a horizontal line which connects two different phases. And if you remember, this purple curve is called liquidus curve and it relates the total vapor pressure of the system at any point with that of the composition of the system in the liquid phase. So, that is why it means the system is only in liquid phase, only first bubble or first trace of vapor gets formed at that situation. So, at all these points on the purple line which represent the overall state, which represent the liquid phase composition, and so is therefore this point A on this purple line or the liquid curve is basically called the point on this horizontal line which connects with the liquidus curve, and point B, contrary to point A, therefore connects to the vaporous curve and therefore represent the vapor phase. So, therefore, these 2 points A and B, from which you can draw perpendicular to the x axis, and therefore, whatever the point comes from point A perpendicular drawn on x axis, so what we get is small xa, that is liquid phase. And since point small b lies on the vaporous curve, so the perpendicular being drawn from point B on the x axis represent the Ya, the composition in the vapor phase. These compositions are intensive compositions. They talk about only the amount fractions, but they do not talk about the number of moles. So, but one thing is very clear. You see, let us say we have a point O, which is called overall state point of the system, and it is well known now from whatever discussion we have carried out till the point of time. From that it is very clear that from point O, if we have this as overall system, and if we want to determine what is the amount fractions of A in liquid and vapor region or liquid and vapor phase, then we should draw a horizontal line, that is called tie line, to connect two different phases, that is liquid phase and vapor phase, and these 2 points which comes on the horizontal line, that is called point A and point B. So, apart from this, we have one very important observation here, that we have a length of line segment OA and we have length of line segment OB as well. Now, if this overall state point is lying very close to point A, it clearly means, as I said, that all the points on purple line indicate where there is the system is in only in liquid phase and only first trace of vapor has formed, and all the points on the blue curve which is the vaporous curve represent the overall system in which there is all the system lies in the vapor phase and only a last bubble of liquid or last drop of liquid is in equilibrium. So, therefore, these two are the different points. So, now we need to understand that is there any relationship between number of moles, that is we will discuss in our subsequent module. Thank you. Alright, in this module we first of all try to discuss lever rule, which relates the number of moles in one phase which is in equilibrium with that of the second phase. So, for this let us first of all consider this vapor pressure versus composition curve that is being drawn for the presence of liquid phase which comes in equilibrium with vapor phase. So, clearly again there is a purple curve that is liquid curve or liquidus curve, and this blue curve that is vapor curve or vaporous curve. We have been having intense details about these terminology in the previous modules. So, now in this region is liquid region and this region is been marked for vapor region below the blue curve, and above the purple curve there is only liquid region. So, now the point is that if we have a line segment AB, which is a horizontal line which connect two different phase lines, one that is liquid phase which is represented by this purple curve, and the other which is represented by vapor phase, that is the blue curve. So, on this line that is the tie line AB, there is a point O which is the overall state point. This can lie anywhere on the line, but it is important to note that if point O coincides with point A, it means in the whole system there is only liquid phase and only a small bubble or very trace amount of vapors are present. If this point O coincides with that of point B, then it means that the system contains only of the vapor phase and only a last trace of liquid or a very small trace of liquid amount of liquid is present. So, it clearly means that it is very important to note that if let us say, you can see from the figure itself, from the phase diagram, if the point A is constantly moved from its position where it is shown in the graph towards the left or to the point A, then the length of line segment OA is decreasing and the length of line segment OB is increasing. Simultaneously, the number of moles of liquid phase is continuously increasing. So, it means number of moles of liquid phase is directly proportional to the length of line segment from the overall state point to that of opposite phase, that is vapor phase OB. So you can say number of moles in the liquid phase is directly proportional to length of line segment OB, and number of mole of vapor in vapor phase is directly proportional to length of line segment OA. In other words, you can also, if we take the ratio and cancel the proportionality constant, then we lead to this relationship, which is nothing but the ratio of number of mole of liquid phase to that of vapor phase equal to lengths of line segment OB and OA. But the point is, what is OB and what is OA? How we can evaluate it? It is very important to note from the phase diagram. You can say that point B represent the value on the x-axis, that is a value YA, and this point O represent capital XA. So it means the difference between amount fraction of component A in the vapor phase and the overall composition of system, that is YA minus capital XA, would be the length of line segment OB, and since point A is represented by capital XA and point A by small xa, then length of line segment OA will be equal to the coordinates to point A minus coordinates to point O and minus coordinates to point A, that is capital XA minus XA. So in this manner, just by using the amount fractions of liquid phase, vapor phase and of overall system, we can determine these lengths of line segments, and we can determine therefore the ratio of number of moles being total number of moles of all the chemical species being present in the liquid phase to that of the vapor phase. And this relationship, which relate the lengths of line segments on the tie line to that of the number of moles present in two different phases, such a relationship is known as lever rule. It is just like the overall state point being represented by fulcrum on a lever, and the lengths, two different lengths onto the two different objects do represent their weightage, or you can say the number of moles in this situation. Alright, having said this, now it is our time to understand some understanding of to achieve some understanding of the numerical aspects of this whole topic which we have discussed till the point of time. And it is the numerical aspects which is very important, because its practical application can be understood only in terms of numerical aspects being understood in this portion. So let us discuss them. So the first numerical, let us first of all we take the first numerical. If suppose that we are given that total pressure of a binary ideal liquid solution is 600 torr at 300 Kelvin. So it means, first of all, let me tell you that if this graph is drawn, and if this graph is drawn at 300 Kelvin, so these extreme points PB naught, PA naught would then be the vapor pressures of two pure components. So we are asked, we have been told that we have been said that if the total pressure of a binary ideal liquid solution is 600 torr, it means some value of pressure on this y axis has been fixed. From that pressure, now determine the vapor pressure values of pure A and pure B. Now we need to know what is the value of PB naught and what is the value of PA naught. If some value of total pressure on this y axis is known, now at 300 Kelvin, it means such a graph should have been drawn at a fixed temperature, that is 300 Kelvin. Now if the further what we are given is that if the mole fraction of A in vapor phase and liquid phase is 0.35 in vapor phase and 0.70 in liquid phase. Now it is important to note that what we need to know. We need to know PA naught and PV naught, and we need to know what we are given. We are given P total, we are given YA, we are given XA. So we should try and use those relationships which relates the total vapor pressure with that of YA and XA, and these two relationships, one in terms of Dalton law of partial pressure. From the Dalton's law we get YA equal to PA by P total, that is PA partial pressure of any gas in a mixture of gases is equal to the amount fraction of the gas in the of the gas in the gases mixture times the total pressure. So, Ya therefore is the, here the gas means the vapors which we have. So, Ya is amount fraction of component A in the vapor phase and is equal to Pa by P total. Pa is partial vapor pressure of component A in the vapor phase. So, now according to the Rolle's law, the vapor pressure of any component is given by its vapor pressure in the pure form multiplied by its amount fraction in the liquid phase. So, it means Ya equal to Xa Pa naught by P total. Now, we can rearrange this formula, we can multiply Ya with P total and divide by Xa, so that we get Pa naught, this value here. So, it means Pa naught equal to Ya into P total by Xa. We are given Xa, we are given Ya is 0.35, Xa is 0.70 and multiplied with total pressure, that is 600 torr, this equal to 300 torr it amounts to. So, Pa naught we have evaluated, that is vapor pressure of pure component A we have evaluated in this manner. Similarly, we can work out this whole formula in place of component in place of component A, we can make use of component B. So, for example, if we want to look for Yb, then this Yb equal to Pb by P total and this equal to Xb Pb naught by P total. Rearranging, it will give us the formula Pb naught equal to Yb into P total by Xb, and Xb, that is 1 minus Xa, and since Xa we are given with 0.70, so 1 minus 0.70 is 0.30, which amounts to Xb. Similarly, we can obtain Yb, that is equal to 1 minus Ya. Ya is 0.35, so 1 minus Ya, 1 minus 0.35 equal to 0.65 into again 600 torr equal to 1300 torr. So, in this manner, it means if we know the vapor pressure of pure components, then and the total vapor pressure, we can get to know the amount fractions. But if we know amount fraction of liquid and vapor phase and we are given total vapor pressure, then we can determine the vapor pressure of pure components as well. Where the application lies, we will discuss it in in the discussion of distillation process, where the main application is the distillation process. So, where there we will discuss all these points. Alright. So, let us have a look at another numerical. If suppose the numerical says that at 333 Kelvin, it means temperature is fixed. The vapor pressure of pure liquid A and pure liquid B are 36 and 118 torr. Please have a look at it. Please note this numerical aspect. At 300 Kelvin means temperature is fixed. The vapor pressure of pure liquid A and pure liquid B are 36.0 and 118.0 torr respectively. If these liquids form a nearly ideal solution upon mixing, determine the composition of a solution of A and B that will boil at 333 Kelvin at a pressure of 50 torr. Okay. So, it means we have to determine the composition, that is of solution, that is composition in liquid phase of component A, that is amount fraction Xa, amount fraction Xb, for a solution that will boil at 333 Kelvin and at a pressure of 50 torr. You see, what is boiling point? We should first of all understand the meaning and we should try to decode the information given in the question itself. He is saying the question is asking us to determine the composition of a solution in terms of amount fraction of component A and B in the liquid phase of, that is the composition of a solution that will boil at 333 Kelvin at a pressure of 50 torr. That means if on the system, if we have a total pressure being exerted on the system is 50 torr and the temperature being maintained is 333 Kelvin, if it is to be true, then we need to explore upon a composition of such a mixture which will boil at this temperature and at this applied external pressure. Point is, we should first of all look at the boiling point, the definition of boiling point. If we get to know the definition of boiling point, then we can probably answer this question, otherwise not. So, first test in this numerical aspect is that we are being tested for our knowledge of the boiling point. Boiling point is the temperature at which the vapor pressure of a particular liquid becomes equal to the external subjected pressure. Now, external or subjected pressure on the system is 50 torr we are given with. So, it means if the system has to boil, this vapor pressure value should match the given or external pressure on which which is being subjected to the system. It means the pressure, vapor pressure of the system should be 50 torr. And if the, now it means what we are given indirectly is that, or in other words, what we are being asked in the question is that determine the composition of such a solution whose total vapor pressure would be 50 torr, but is asked in a way that determine the composition of such a solution whose boiling point is 333 Kelvin at this pressure. So, from this information we have decoded by this discussion that what we are given is actually the value of total pressure which is being subjected onto the system, and that is equal to vapor pressure of the system, and therefore, our total vapor pressure, we are actually given with the value of total vapor pressure, that is equal to 50 torr. So, now this 50 torr is the total vapor pressure which we have decoded. Once we have done that, what else we are given with? We are given with vapor pressure of pure components, the two component in the binary solution, that is vapor pressure of pure component A. We are also given with vapor pressure of pure component B, that is PA naught and PB naught. And now if we know total vapor pressure of solution, that is P total, and we also know the vapor pressure of pure components. So, if you recall back, we had derived a formula in this manner. Please have a look at it. You see, total vapor pressure of a binary liquid solution is given by the equation P total equal to PA plus PB, that is partial vapor pressure of component A plus partial vapor pressure of component B. So, we know from Rolle's law that PA equal to XA PA naught and PB equal to XB PB naught, if you remember. That we had discussed in our first lecture in the solution chapter. So, we had substituted these two values from the Rolle's law. So, P total equal to XA PA naught plus XB PB naught. So, P total equal to now XA PA naught plus, instead of XB we can write 1 minus XA into PB naught. So, we can take XA common from this term and first term and last term. What we get is PB naught plus PA naught minus PB naught into XA, and now we can rearrange it. We can take PB naught to left and left side equal, it leads to P total minus PB naught equal to PA naught minus PB naught into XA. So, now we can take this bracket term to the denominator of left hand side LHS. So, what we get is XA equal to P total minus PB naught divided by P naught minus PB naught. So, now what information we are given? Please recall, in the given data in the numeric problem, we are given the P total value, but in an indirect manner. We have decoded the information and we have come to the conclusion that whatever is the total pressure which is on which the system is subjected to, that is actually our vapor pressure at equilibrium when boiling occurs, and as a result 50 torr is our total vapor pressure. So, P total is 50 torr. PB naught we are also given, PA naught we are also given, PB naught is 118 torr and PA naught is 36 torr as the information given in the numeric problem itself. So, therefore, we have seen this information, we can just plug in the value of PB naught 118 torr, PA naught 36 torr, again PB naught 118 torr and P total 50 torr. That is it, and just determine XA, the composition of the liquid phase, or in other words the amount fraction of component A in the liquid phase, that is equal to 0.82. If you want to determine XB, then XB equal to 1 minus XA equal to 1 minus 0.82 equal to 0.18. So, what I mean to say is, if we are given with total vapor pressure and vapor pressure of pure components, we can determine composition of solution. If we are given with composition in the liquid phase, then we can determine the total vapor pressure as well. So, these two informations are related to each other, and we can, if we know the one, we can get to know that of the other. That is it. That is what we can obtain from these numeric problems. But what is important is the following. If you recall back, we had discussed the vapor pressure versus composition curve, and there we had said, let us have a look at it again. From the vapor pressure versus composition curve, just have a look. If we have a overall system represented by point capital O dash, this point, this represent overall state of the state point of the system. It means the system is maintained at very low pressure and the system lies only in the vapor phase, because this point O, capital O dash, lies below this vaporous curve. So, only liquid phase. If we raise the pressure on the system by decreasing the volume of the system, then the pressure of the system will increase, because the same amount of the gases mixture, when is subjected to lower volume, its pressure will gets raised. So, upon increase in pressure, the overall state point of the system will continuously move upward on this blue vertical line. Please have a look at it from the phase diagram itself. And when we continuously keep on doing so, that is raising the pressure on the system, then eventually a point will reach, that will be the point on the vaporous curve. At this point, at this point where this pointer is pointing out to be, at this point, now you will have at this point formation of condensate, starting of formation of condensate, that is first droplet of liquid will form, and when you continuously keep on raising the pressure on the system, ultimately point O will reach. And now you can look at it very clearly from point O. If you draw a tie line at point O, if point small o, here this point, if this point represent the overall state point of system, at this point you will have, since this point lies within the liquid region and the vapor region, so we can say at this point there are two different phases which are in equilibrium with each other, and when these two phases are in equilibrium with each other, then it is clearly a situation that we should have composition of both the phases. That, as I discussed earlier, these two compositions can be obtained by drawing a tie line from point O onto the two different phases. These 2 points becomes point A small a and point small b on this vapor pressure versus composition curve. So, AB is the tie line, and therefore from this tie line, point A represent composition of liquid phase, point B represent the composition in vapor phase. You can notice it very clearly and very carefully that Ya has value which is greater than value of small xa, and small xa is also lesser than overall composition. So, what I mean to say is, you had started with a particular composition, particular mixture of A and B. Let us say if you had mixed 1 mole each and it has led to formation of a mixture with capital XA equal to 0.5, that is proportion of both components are equal in overall system. But when you subject it to and take it to point O, which remains represent the overall state point of system. At this point, there occurs emergence of or two phases which are in equilibrium with each other, and both these phases will have different amounts of the two components. Vapor phase will be richer only in that component which will be more volatile. It is very simple. So, you can see from the phase diagram phase diagram itself. Here you can see component A is more volatile because vapor pressure of pure component A is greater than that of vapor pressure of pure component B, and therefore you can see the point B, which represent composition of the vapor phase, has value of Ya greater than value of small xa. It clearly means the component A is more volatile and its amount or its proportion is greater in vapor phase compared to that of the liquid phase. So, we can conclude that whenever a liquid phase comes in equilibrium with the vapor phase is relatively richer in the more volatile component. That is what we obtain from this phase diagram. We can also prove it mathematically. We have developed the relationship, if you recall back couple of in the previous lecture, that Ya, the amount fraction of component A in the vapor phase, can be related to according to Dalton law of partial pressure to Pa by P total, and Pa can be obtained in terms of Rolle's law as XA Pa naught and P total in terms of XA Pa naught plus XB Pb naught. Now, so therefore, this is the relationship of Ya. Now, if we divide this first expression by Xa, what we get is Ya by Xa at left hand side, and on right hand side we get rid of Xa. If we further divide it with respect to Pa naught, so we also get rid of Pa naught in the numerator at the right hand side, and what we get is over here as Pa naught from the denominator of Xa Pa naught also, and again we have Xb Pb naught, but having it divided by Pa naught. So, what I mean to say is, if we divide the whole expression by Xa Pa naught, so ultimately what we have is this value. What value? That is Ya by Xa equal to 1 by Xa plus Xb Pv naught by Pa naught. Now, if we say component A is more volatile, what does it mean? It means that vapor pressure of pure component A is greater than that of vapor pressure of pure component B, that is Pa naught is greater than Pv naught. Then in that situation, let us look at this expression. If Pb naught is less than Pa naught, then this ratio Pb naught by Pa naught will always be less than 1. Xb amount fraction, if you know it, if you recall back in first lecture, Xb would always be in a binary mixture would always be less than 1. Similarly, Xa would also be always less than 1. So, this whole denominator would be a fraction which will be amounting to a value less than 1. So, any one numeric value 1 divided by a value less than 1 will lead to a some magnitude which will be always greater than 1. It does mean Ya will be equal to some value greater than 1 multiplied by Xa. It means Xa therefore will always be less than Ya. So, it clearly indicates that composition a proportion of component A would be more in the vapor phase compared to its proportion in the liquid phase if the component A is more volatile. So, what we can conclude from this little derivation and this little phase diagram illustration is that when a liquid phase comes in equilibrium with the vapor phase is relatively richer in the more volatile component, or more volatile, the proportion of more volatile component is greater in the vapor phase compared to that in the liquid phase. Or in other words, we can also say the proportion of a component will be greater in vapor phase if its addition to the liquid mixture leads to an increase in the total vapor pressure. So, these two conclusions comes under the Novolov rule, and they makes the foundation for the isobaric distillation process that we will discuss in the next module. Thank you so much.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Kumar for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.